The topic of this video is Newton's law of gravitation. Probably the most famous force of all is gravity. We humans on Earth think of gravity as an apple hitting Isaac Newton on the head. Gravity means that stuff falls down, but this is only our experience of gravity. In truth, just as the Earth pulls the apple towards it due to a gravitational force, the apple also pulls the Earth as well. The thing is, the Earth is just so massive that it overhangs all the gravity interactions of every other object on the planet. Every object with mass exerts a gravitational force on every other object. So the Earth pulls the apple towards itself, and also the apple pulls the Earth to itself. According to the Newton's law of gravitation law, every single point mass attracts every other point mass with a force directly proportional to the product of the masses and inversely proportional to the square of their separation. So M2 pulls M1 towards itself, M1 pulls M2 towards itself. The force exerted by the first object on the second one is equal to the force exerted by the force of second object on the first one, but they're opposite in direction. And according to Newton, this force is equal to a gravitational constant directly proportional with the multiplication of the masses and inversely proportional with the square of the distance between them. So in the formula, F is the force of gravity between the two objects, which is in Newton. M1, the mass of the object 1 in kilogram. M2, the mass of the object 2 in kilogram. R is the distance between their center of masses in meter. And G is a universal gravitation constant, which is equal to 6.67 times 10 to the power minus 11 Newton meter square over kilogram square. In this example, here two objects apply a force of F, which is equal to G times M over the distance square. And we are going to compare the other three examples. In the first one, you see that the second object has a mass of double volume, so the new force will be equal to G times the mass of 1 times the mass of 2 over the distance square. So you see that this value is twice the initial one, so you see the force is doubled. In the second example, both of the objects' masses are doubled, so the new force is equal to G times 2m over d square, which is equal to 4g m over d square. So this value is 4 times the initial one, so the force increased by 4. In the third one, only the second has a mass of 3m, so the new force will be equal to G times m times 3m over 3 square. So this value is again the 3 times the initial one, which is equal to 3f. Now let's put the relation with the distance. Again, we have objects. They attract each other with a force of Gm over d square. In the first example, the distance is doubled, so my new force will be equal to Gm over 2d square, which is equal to Gm over 4d square. So this value is 1/4 of the initial value, which is equal to f over 4. Now here the distance decreased by 2, so my new force will be equal to Gm over d over 4 square, which is equal to Gm over d square over 4. 4 goes up, so is equal to Gm over d square. So this value is 4 times the initial one. And in the last one, both the masses are doubled and the distance also doubled. So my new force will be equal to G2m times 2m over 2d square, which is equal to G4m over 4d square. So 4 cancel each other. So you see that I have the same value with the initial one. So it is again equal to F. In the example, the gravitation force between the given masses is 20 Newton. So first, what will the value of F be if we double both the masses and half the distance between them? So our initial force is equal to G m1 times m2 over r square. The new force is equal to G double the masses 2m1 to m2 over half the distance, so r over 2 square, which is equal to 16g m1 m2 over r square. So this value, you see that is equal to 16 times the initial one. So as F is equal to 20, 16 times 20, which is equal to 320 Newton. In B, what will be the value of FB if we half the masses and double the distance? So new force is equal to G half the masses m1 over 2 times m2 over 2 over the double distance 2r square, which is equal to 1 over 16 times G m1 m2 over r squared. So this is equal to F. So new force equal to F over 16. When we put the value F as 20, it is equal to 20 over 16 Newton. In C, if the mass of each object are doubled, what should the distance be in order not to change the gravitation force between them? So the initial value will be equal to the new value. The initial value is G m1 m2 over r squared. The final value G double the mass, so 2m1 times m2 over 2m2 over the new distance square. So G cancel each other, m1 m2 cancel each other, so I have x squared is equal to 4r squared. So x is equal to 2r. So if I double the distance, then the new force will again be the same.